Welcome students to the MOOCs lecture series on statistical inference. This is lecture number 20. If you remember, we are doing testing of hypothesis as the last topic of the series of lectures. So, testing of hypothesis means we have some statement about the value or values of the parameters and we seek support from sample say of size n, whether the statement can be accepted or rejected in favor of some alternative. So, that is the whole purpose of testing of hypothesis. Our aim is to divide the entire sample space into two parts: acceptance region and rejection region. Say for example, we want to test whether a coin is unbiased. So, if we look at a simple null hypothesis, then our H naught is p is equal to half, and we are testing it against an alternative hypothesis H 1 p is equal to say 0.25 or 1/4. Suppose we decide to toss the coin. Hundred times. Then what is going to be the sample space? So, the sample space is and each member of the sample space is a string of length 100 and each element is either 0 or 1. Therefore, there are 2 to the power 100 such strings in the sample space. Suppose these are the points in the sample space. Now, our job is to design a critical region. Or rejection region. Say we decide this is to be our critical region, so that if the outcome is falling in this part of the sample space, then we are going to reject the null hypothesis. So, this is called W, and this side is called W complement, which gives us the acceptance region. Now, the W and W complement depend upon both H naught and H 1. Say H naught is half, as I have already mentioned, and H 1 is 1 by 4. And suppose number of heads in 100 tosses is equal to 40. Now, 40 heads can be achieved for both H naught and H 1. Therefore, our job is to identify the probability of getting 40 heads under H naught and H 1. Perhaps it is okay to reject H naught in favor of H 1 when number of head is 40. But if the number of heads is 60, then perhaps it is not wise to reject the null hypothesis H naught in favor of H 1, that P is equal to 1 by 4. On the other hand, if H 1 is P is equal to 3 by 4, then it may be wise to reject H naught p is equal to half in favor of H 1, that p is equal to 3 by 4. So, the job of a statistician for testing of hypothesis is that we have to decide the test so that we know the sample space, and we need to decide the testing criteria so that we can accept or reject the null hypothesis against an alternative. So, as I discussed, two types of possible errors. One is type 1 error, which we call alpha, that is rejecting the H naught when H naught is true. That means, actually the coin is unbiased, but we are rejecting that hypothesis based on the sample obtained. And if I reject when the H naught is true, then we are committing an error which we call type 1 error. And type 2 error is which we call beta, is accepting H naught when H naught is false. Ideally, we should minimize both, but as I have explained that cannot be done. Therefore, we put a bound on type 1 say 5% or 1%. That means, we can make a mistake only 5 out of 100 cases or 1 out of 100 cases, and within that we try to minimize beta or maximize 1 minus beta. This quantity is called the power of the test, and when both H naught and H 1 are simple, the test having maximum power is called the most powerful test. So, definition: a critical region W is said to be most powerful to test H naught theta is equal to theta naught versus H 1 theta is equal to theta 1 when the size of the critical region is alpha such that probability x belonging to W given theta is equal to theta naught is equal to integration over W L theta naught of x 1 x 2 x n dx is equal to alpha. So, we are saying that the making the mistake of rejecting a correct null hypothesis is this probability that the obtained sample x will belong to the rejection region or critical region W. These probabilities integrating on the space W of L theta naught x 1 x 2 x n. This is the joint PDF of obtaining the sample x 1 x 2 x n under the null hypothesis, that is the parameter theta is equal to theta naught, and that probability should be alpha. And among all critical regions W 1 of size alpha, integration over W of L theta 1 of x 1 x 2 x n dx is greater than equal to integration of W 1 of L theta 1 of x 1 x 2 x n dx. This is because we want to maximize 1 minus beta. What is beta? Beta is equal to probability of type 2 error is equal to probability of accepting H naught when H 1 is true. Therefore, 1 minus beta is equal to probability of rejecting H naught when H 1 is true is equal to probability that the sample x 1 x 2 x n belongs to the critical region when H 1 is true, and therefore, this is equal to integration over W L theta 1, because H 1 is true, the parameter is theta 1, and this is x 1 x 2 x n dx. Therefore, if this is the sample space, and suppose this is one critical region W, and this is another critical region, say W1, such that both of them are of size alpha, but the probability of type 2 error is least for W for any such W1 of size alpha. In this respect, question is, what will be the structure of the most powerful region? Or in other words, which function of the sample x1, x2, xn we should take, so that based on that we can make the decision of rejecting or accepting the null hypothesis, and the corresponding test is most powerful. In this respect, the most important result is called Neyman-Pearson lemma. Today, I will give you the lemma and solve a few problems based on the Neyman-Pearson lemma. In the next class, I shall give you the proof of the lemma, so that you can understand how such a result has come. Neyman-Pearson lemma. Suppose we are testing two simple hypotheses H naught theta is equal to theta naught versus H 1 theta is equal to theta 1, and we have taken a sample x 1, x 2, x n, then Neyman-Pearson lemma suggests that if L theta 1 x 1, x 2, x n is the likelihood function of the sample under H 1 and L theta naught x1 x2 xn is the likelihood function of the sample under H naught, then according to Neyman-Pearson lemma, the most powerful critical region will be such that L theta 1 of x1 x2 xn upon L theta 0 x1 x2 xn is greater than k for some positive, or say greater than equal to k for some positive constant k. The value of k will depend upon the pre-decided size of the test, that is alpha. So, at the beginning, as a statistician, one will decide upon the size alpha, whether it is 5% or 1% or 10%, and based on that we should get a constant such that L theta 1 of x1 x2 xn upon L theta naught of x1 x2 xn has to be greater than that constant. Before proving that, as I said, in today's class I will solve a few problems using the above Neyman-Pearson lemma. Let us consider the first example. Suppose we are tossing a coin, so we are looking at Bernoulli P distribution, and we are testing say H naught P is equal to 0.5 or half versus H 1 P is equal to 0.75 or 3/4. Therefore, by Neyman-Pearson lemma, the most powerful region, critical region, will be L say 3/4 of x1 x2 xn upon L half of x1 x2 xn is greater than k, where x1 x2 xn is the sample. Now, L 3/4 of x1 x2 xn is equal to 3 by 4 to the power sigma xi into 1 by 4 to the power n minus sigma xi. This we have seen as probability x is equal to 1 is equal to p to the power x 1 minus p to the power 1 minus x, where x is equal to 0 or 1, which comes from Bernoulli trial. Similarly, L half of x1 x2 xn is equal to half to the power sigma xi into half to the power n minus sigma xi. Therefore, L 3 by 4 of x1 x2 xn upon L half of x1 x2 xn is equal to 3 by 4 to the power sigma xi into 1 by 4 to the power n minus sigma xi into half to the power sigma xi into half to the power n minus sigma xi, and that has to be greater than equal to k, or 3 by 4 to the power sigma xi 1 by 4 to the power n minus sigma xi is greater than equal to k times half to the power n, or 3 by 4 to the power sigma xi upon 1 by 4 to the power sigma xi into 1 by 4 to the power n is greater than equal to k into half to the power n, or 3 to the power sigma xi is greater than equal to k times 2 to the power n. By taking log base 2, we get sigma xi log 3 to the base 2 is greater than equal to log k plus n, or sigma xi is greater than equal to log k plus n upon log 3 by 2. This is a constant, let me call it C. Therefore, the critical region will be of the form sigma xi is greater than equal to a constant C, or in other words, we will reject the null hypothesis that the probability of a head for this coin is half. We will reject that in favor of that the probability of getting a head is 3 by 4 if sigma xi or the number of heads is greater than some constant, which is very intuitive, because the alternative here is 3/4, which is bigger than the null hypothesis value, that is half. So, in general, the critical region for Bernoulli P will be from NP lemma as follows: P1 to the power sigma xi into 1 minus P1 to the power n minus sigma xi upon P0 to the power sigma xi into 1 minus P0 n minus sigma xi is greater than equal to k, or P1 upon P0 sigma xi into 1 minus P0 sigma xi upon 1 minus P1 sigma xi is greater than equal to 1 minus P0 to the power n upon 1 minus P1 to the power n times k. This is the general structure. So, depending upon whether P1 is greater than P0 or P1 is less than P0, we shall get two different types of critical region. As we have seen, if P1 is greater than P0, the shape of the critical region will be sigma xi is greater than some constant. I leave it on you, you verify that if P1 is less than P0, then the shape of the critical region will be sigma xi is less than some constant c. The question is how to obtain c. When n is small, for a given alpha, we can determine is easily as follows. Say n is equal to 10, and we have alpha is equal to say 0.05, that is 5%, and with respect to the earlier problem, our CR is sigma xi is greater than some c. Now, under H naught, that is p is equal to half, probability sigma xi is equal to 10 is equal to half to the power 10. Probability sigma xi is equal to 9 is equal to 10c1 half to the power 10 is equal to 10 divided by 2 to the power 10. Probability sigma xi is equal to 8 is equal to 10c2 half to the power 10 is equal to factorial 10 upon factorial 8 factorial 2 into half to the power 10 is equal to 45 upon 2 to the power 10. Therefore, probability sigma xi greater than equal to 8 is equal to 1 plus 10 plus 45 half to the power 10 is equal to 56 upon 1024, which is roughly equal to 0.05. Therefore, with respect to the problem, our critical region with alpha is equal to 0.05 to test p is equal to half against p is equal to 3 by 4 is sigma xi is greater than equal to 8. Or if number of heads obtained is 8 or more, then we are going to reject the null hypothesis that the coin is unbiased. Otherwise, we are going to accept that this coin is unbiased when testing against p is equal to 3 by 4. In a similar way, we can check that if H naught is p is equal to half, but H 1 is p is equal to 1 by 4, then the 5% level critical region will be reject H naught if sigma xi is less than equal to 2. That is, number of heads is equal to 0 or 1 or 2, then reject H 1, reject H naught in favor of H 1 p is equal to 1 by 4. If the number of samples is large, then we can make normal approximation say n is equal to 100. Therefore, under H naught expected number of heads is equal to 50 and variance of sigma xi is equal to 100 into half is equal to 25. Therefore, sigma xi minus 50 upon root over 25 may be approximated as normal with 0, 1. Therefore, the 5% critical region is modulus of sigma xi minus 50 upon 5 is greater than equal to 1.65. This can be obtained from the normal table. Therefore, depending upon P1 is greater than P0 or P1 is less than P0, we shall decide the acceptance or rejection of H naught if 50 minus 1.65 into 5 is less than equal to sigma xi is less than equal to 50 plus 1.65 into 5. And we know that if P1 is greater than P0, then this should be the condition. If P1 is less than P0, then this should be the condition. Therefore, the shape of the critical region will be obtained accordingly. Let us now consider a second example. Suppose we have observations from exponential lambda, and our H naught is lambda is equal to lambda naught and H1 is lambda is equal to lambda 1. What will be the most powerful critical region? Using Neyman-Pearson lemma, L lambda 1 of x1 x2 xn, L lambda 0 of x1 x2 xn is greater than equal to some positive constant k, or lambda 1 to the power n e to the power minus lambda 1 sigma xi upon lambda 0 to the power n e to the power minus lambda 0 sigma xi is greater than equal to k, or lambda 1 upon lambda 0 whole to the power n e to the power minus lambda 1 minus lambda 0 sigma xi is greater than equal to k. Here also shape of the critical region will change depending upon lambda 1 is greater than lambda 0 or lambda 1 is less than lambda 0. Consider lambda 1 is greater than lambda 0. In particular, let lambda 1 is equal to 2, lambda 0 is equal to 1. Therefore, by NP lemma, 2 to the power n e to the power minus 2 sigma xi upon 1 to the power n e to the power minus sigma xi is greater than equal to k, or 2 to the power n e to the power minus sigma xi is greater than equal to k, or e to the power minus sigma xi is greater than equal to k upon 2 to the power n. Let us call it a constant equal to c. By taking natural log minus sigma xi is greater than equal to some constant, or sigma xi is less than equal to some constant. Because this is negative, there is a change in the inequality. Now, we need to determine the constant. Under H naught, sigma xi is equal to gamma 1 comma n. Therefore, we need to integrate the gamma PDF for lambda is equal to 1 and alpha is equal to n to obtain the value of the integral. In a similar way, we can take care of different problems. In particular, suppose we have normal mu comma sigma square, where sigma square is known. Then the shape of the critical region will be determined as follows. So, L1 upon L0 is equal to e to the power minus 1 upon 2 sigma square into sigma xi minus mu 1 whole square upon e to the power minus 1 upon 2 sigma square sigma xi minus mu naught whole square when we are testing H naught mu is equal to mu naught versus H 1 mu is equal to mu 1. I like you to verify that if mu 1 is greater than mu naught, then the critical region will be x bar is greater than equal to sigma square by n log of k mu 1 minus mu naught plus mu 1 plus mu naught by 2, that is x bar has to be greater than equal to lambda 1, which is a constant, and if mu 1 is less than mu naught, the CR will be x bar less than equal to lambda 2 constant. And we can obtain the value of lambda 1 or lambda 2 by using the normal table. So, this is how we decide whether to accept a simple null hypothesis against a simple alternative hypothesis when the distributions are known. If the statistic is such that we know its PDF and we get its table, then we can obtain the value from there. Otherwise, we will have to integrate the PDF, or you have to numerically obtain the value of the threshold, so that depending upon whether the statistics is greater than that or less than that, we can take a decision of accepting or rejecting the null hypothesis. Okay, friends, I stop here today. In the next class, I shall prove the Neyman-Pearson lemma and also solve a few problems to understand the method of testing of hypothesis. Thank you.